Okay, so we start? Yeah. Okay, so today we have Christian van den Broek, for a close approximation to the way you pronounce his name. He's laughing, so it's not too good. He's from the Hasselt University in Belgium. He did his PhD in Brussels University in the early 80s, Pregogin's group. Then he moved to Austin and then to the University of San Diego. He worked with Institute. He's worked on many things related to basic aspects of statistical physics. He's heavily works on stochastic processes, then on ratchets, Brownian motors, neural networks. His celebrated work on noise-induced phase transitions, very important. And most recently, he's been doing work on the second one. I should say that since Boltzmann stated the second law, there have been thousands of papers. I've been following about the second law. I've been following recently like how to teach the second law. So something to forget about. And I feel that people have been going in circles. I've read many things saying the same again and again and again and again. And then for the first time, I think people are beginning to say new things that were not said before. So I want to tell you how this spectacular result is.
So it's a great pleasure to be back here. Of course, I spent sometime in my young years, I spent meetings in Spain, and I met many people here about friends. And we worked, many of us worked on stochastic processes, and we did more applied statistical physics, or including statistical physics. And so for me, it's a surprise that during the last few years, like the last 5 years, I was able to return to the basic questions that I wanted to attack when I was young. I was afraid to do at the time. So now, of course, I'm old enough to do this, and the surprise is that I think there are really, as Maxi mentioned, the word spectacular. For me, I think really spectacular developments to which I participated, and so I would like to give you a little bit of tips into these developments. I will also, at the same time, make a little bit of publicity about my other things that I did, which are related to these basic issues, but this will be in the introduction. I will mention some other things that may be of interest to several of the people here. Okay, so as a matter of introduction, let us go back to the origins of science. These are the alchemists. They were interested in basic, very important basic questions, and they, of course, they identified already what were important questions. One of the basic questions is, of course, the question of money, making gold. The other was also the question of living long. So, and they were looking for the alchemist's stone, which was supposed to provide opportunities to solve all of these problems. What is less known is that they also realized that energy is a very important entity, even though they didn't know what energy was at the time. But for instance, they wanted to make perpetuum mobiles. And here I give you 3 examples of proposals for perpetuum mobiles, a mechanical and magnetic one, and this is a chemical one. They were interested also in this issue. Okay. Of course, now we are a little bit further. We have made some progress, and we know that the transmutation of elements is possible. Actually, it occurs spontaneously in the stars, and we do it in our nuclear reactors. We have also, by now, identified the elixir of life, Belgian beer. But nobody has so far been able to make a perpetuum mobile. So this is the main important issue that they have not been able to solve. Of course, when something is impossible, as a scientist, we know that it means there will be something very deep behind it. And of course, we now know that there are 2 kinds of perpetuum mobiles, and associated to each of them, there is a very important physical principle. First is that there is no perpetuum mobile of the first kind, which is the conservation of energy, which is somewhat related probably to the fact that the laws of nature are invariant under translation in time. And the other one is the perpetuum mobiles of the second kind. This means that you can, for instance, not extract work out of a single heat method. And you know, of course, this second principle, the non-existence of the model of the second kind, is actually the origin of thermodynamics of the second law. And just for purpose of history, of course, I mentioned here, I will come back to that, I mentioned this beautiful work by Parrondo, the French engineer, who realized that from the fact that you cannot expect work out of a single reservoir, you can say something about how much work you can extract when you have two reservoirs of your storm. So it's a really very, very beautiful piece of work which will make some of you teaching your classes. So he was able to show that if you have two reservoirs at different temperature, there is something like an efficiency, which is the amount of work you get, compared to the amount of heat that is extracted from the hot reservoir. So the temperature of the hot reservoir is TH, the other is TC. And he showed that this ratio is at best 1 minus the ratio of the temperatures. This is, of course, a famous concept of Carnot efficiency. He took Lapeyron, because he did, Carnot died early, it was Lapeyron who actually publicized his work, and it was Clausius who realized that this innocuous statement about thermal motors also means that you can define a new state variable, which is the entropy. I mean, actually, for the case of these thermal machines, for those who remember that you have all these cycles here, the system returns to the same situation, and so the only thing that happens is that there is heat going from the hot reservoir to the cold reservoir, and it turns out that this statement, that this efficiency is smaller than the Carnot efficiency, is saying the same as what we now know, of course, that the total entropy in the device can only increase. The total entropy in the device, the system entropy does not change because you're going back to the same state. This is the entropy increase in the hot reservoir, this is the entropy increase in the cold reservoir. This is exactly the same statement as that. If you put in this quantity to the work and eliminate the QC, you get exactly the same. And of course, we know this goes much further. You can kind of make a statement in general that the total entropy increases. And this is, of course, many implications for science and even beyond this. This is, by the way, is not my office. But as a theoretical physicist, you always choose the best example to illustrate your theory. Now, so this is second law. These are, in a sense, already when I say many phases of second law, the absence of the perpetuum mobile of the second kind. It's the first expression, Carnot efficiency is the second expression. This entropy increase is the third expression. And there are, of course, more results that have been derived. I want to mention here because they will also be relevant in the story that I will continue to tell. Is that if you also to get Carnot efficiency, you know that you need equality sign. And equality sign means that you don't have entropy production at all, so you have a completely reversible situation. People were then interested in seeing what happens if you go a little bit out of this reversible situation, and then we have to thank Onsager and Prigogine who introduced this theory of linear irreversible thermodynamics. So if you're outside of equilibrium, you have entropy production, so you have entropic forces and flows, and they developed this beautiful theory of linear irreversible thermodynamics with Onsager. For those who know this, of course, he showed that the reversibility of the underlying laws implies that the coefficients, these coefficients here of response, have a symmetry. So this L12 is equal to L21, which, for instance, if you want to make it concrete, because I will use this statement later on, if this is a thermal process and this is a mechanical process, then you see this is the force associated to the this is the force associated to the mechanical process. So this is a real force. This produces a flux, thermal flux, and this is here the force associated to the thermal process, which is gradient of temperature. This produces a motion. So what you actually have is this element is what you would call a thermal engine, and this element would be a refrigerator or a heat pump. And so what Onsager showed is, in a sense, if you have a construction in which you have a thermal engine, then you should also be able to make a refrigerator. Okay, well, what has happened? So people have worked on the second law, as was mentioned by Joule, for many, many years. And it's very strange because thermodynamics is normally represented as a theory for macroscopic systems, and many people believe that thermodynamics is only something to say for macroscopic systems. But it is because we are now interested in small-scale systems for biological reasons, for nanotechnology reasons, that actually we have made a completely new discovery, a new formulation of the second law, as I already mentioned. So I say small is beautiful. This is me, of course, here. And so what we now need to do is we ask the question, what can you say about these thermal engines, for instance, about Carnot engines? If you talk not about big engines, not about macroscopically big engines, but about small engines. Okay. Okay. Well, this question is also not really new. You see, this is here the bay of not the bay of Palma, but it's a bay that I hope to develop soon here. And so you can ask following question: can you, if this would be a reservoir at equilibrium, which it is not really, but okay, can you expect work from it? Not using a macroscopic engine, but a small-scale engine. Maybe this thermodynamics does not apply to small-scale engines, and so maybe I can do so. Actually, this idea is not new. I mean, Maxwell already had this idea that maybe if I have an intelligent being, a kind of Maxwell demon, I should be able to extract work out of a single reservoir by separating, because I can observe them, the hot particles from the cold. Even though in the beginning they are mingled, I could open and close the door so that I could produce a thermal gradient by letting pass cold one side and hot the other side, and then I could extract work. Another version of something similar was actually Smoluchowski. This is here, paper 1912. He said that this probably doesn't work, and he produces a more mechanical. This is, of course, a little bit of a problem how to describe a demon. And actually, these days, we are very much involved into that. But I think I cannot really talk about that today. So they made a mechanical device that has somewhat the same impression from the macroscopic side. Such a device, it's like what you have in your watch. It only seems to rotate in one way. If it only rotates in one way, and you have collisions because of the thermal motion, you have the impression that it will rotate one way because it cannot rotate the other way. So you will be able to extract work out of the single reservoir. And this was studied, this model was studied by Feynman, and he's mentioned in his lectures. There's actually a mistake in his analysis, and one another Parrondo and Espanol from here today were one of the first people to point out this error. I will come back to that also. So anyways, we don't believe this is possible, even though at a small scale, of course, the world looks very different. And so we have to reconsider everything at a smaller scale, and we can ask a lot of questions, and I will actually mention 3 topics here. This is the main topic because I want to tell you what are these new developments about the second law when you look at small-scale systems. But very quickly, I want to say something about, because this is to advertise my own work, and maybe to mention it to people who would be interested. So we say something about Brownian motors, especially about Brownian refrigerator, and I also want to say that something is actually related to this. I will explain how, but I want to say something about this efficiency issue that Carnot started with. So, Brownian motors. So, what I want to present here is a work that I did already several years ago. As I mentioned, Feynman gives an analysis of his construction in his book where there is a mistake in his analysis. And this mistake was recognized by other people. And actually, so with the Feynman construction, you cannot reach Carnot efficiency. So one of the things I did is I wanted to make a model of this problem that can be studied exactly from a microscopic point of view. So the analysis that Feynman gave was somewhat hand-wavy. So let me explain you what is the model, because I think it's interesting. So what is the idea of Feynman? So you see you have this construction here which gives the impression you can only go one way. But of course you have to describe all these things here. And in order for this object to be able to rotate, this spring here has of course to be very weak because it has to allow to lift over the barrier by collisions that are from single particles. And as this is a very small live object, it will fluctuate itself, and so sometimes the things go both ways. It's of course very complicated to model. So what I did is I basically take the basic ingredients of this Feynman-Smoluchowski equation. What are the basic ingredients? The basic ingredients is that you have two reservoirs, which I do. I have one reservoir here and one reservoir there. And the other ingredient, I have an asymmetry. And I don't work in 3 dimensions, I work in 2 dimensions. So what I have is, I have here one object which consists of an arrow with a paddle, which form 1 degree of freedom. It's one object, one rigid solid object with no internal degrees of freedom. And then I have a gas of particles here and a gas of particles there. And so I have nothing outside, it's a completely isolated system, but these particles start at different temperatures. If they start at the same temperature, then you should not be able to extract work. This means that this object here should not be able to move systematically in one direction, because then I would pull away to it. If the temperatures are different, we should be able to do that. And so we did both an exact analytic calculation for the speed of this object in the limit that these reservoirs are infinitely large and that the particles are ideal gas. You can calculate this using kinetic theory, and it's an exact result. And this is an expression actually we can calculate for any shape of the object. But so, and then we did molecular dynamics. So these are just hard disks. There is nothing outside, no other reservoirs. They just start at different temperatures. And this is the laws of Newton that you see here acting. And this object is just 1 single degree of freedom. And because originally the temperature here is slightly higher than there, actually this object, it moves in a Brownian way, but it has a systematic motion, which I get you to derive. Okay. So this is to tell you that if you ever hear about the Feynman method, this is a microscopic version of the Feynman method, which we can solve analytically. We have a simulation and so on.
But what drives this object upstairs? Because you must have a gradient somehow. Because
the temperatures are different.
No, but you have a...
No, you don't. No, you don't have a gradient in that direction. This is the point. You have, the only ingredients you need is that the temperature below and above are different, and an asymmetry of your object. That's all you need. So it is, as a result of that, object will actually move systematically in one direction. This we calculate with simulation again.
I'm sorry?
This is
This exact result.
Yes, this is an exact result. I mean, this is a simulation. I mean, these are the exact results, and these are the result of the Monte Carlo hard disk simulations for the speed as a function of the difference of time. I just want to mention this here for those who are interested, because I worked on it. It's not the main part of my topic, but actually, it's also not the main part of this slide. Because, okay, many people work on Brownian motors, and so it's nice to have an exact resolvable model. But what I, yes?
So what would happen if you wouldn't have the second reservoir at all? Only had this?
Then it just performs Brownian motion, and there's no refractification. So if the two temperatures are the same, the speed is 0. Also, if you have one reservoir, the speed will be 0. But you have Brownian motion of this object, it will perform. So if you have an asymmetric object in a reservoir, it will not rectify. It just will perform a part. We can calculate the diffusion coefficient. It is because you have two different temperatures. You have the ingredient of a thermal engine, and you have asymmetry. Therefore, you have rectification. Now, what I wanted to mention is, because I think this is, of course, there is a whole field on Brownian motors, and it's not my topic. But something that we realize is, as I mentioned in the introduction, when you have a thermal engine, because of on-cycle symmetry, you also have a refrigerator. What is nice about this thermal engine is not a normal engine because it's driven by fluctuations. Actually, I forgot to tell that. If the mass of this object here, the mass of the object is here, if this mass becomes very, very large, the speed goes to 0 as it stops working. So it works because of fluctuations. Because of on-cycle symmetry, if you have a thermal engine, you also have a refrigerator. So what we did is, I'll just tell you the result, okay? So it comes from on-cycle symmetry, and because of the technological interest, we did calculations here, not in 2D, but in 3D, not for a translational motion, but for a rotational motion, because that is what you would like to make. So this is my refrigerator, the smallest refrigerator in the world. So it's a chiral object, okay? It's with a sheet here, and so I have here I don't really need a sheet. So what is the thing? If I have a sheet, if I have a difference of temperature, according to my theory, we can calculate, we can verify, this object will start to rotate. This is a Brownian motion. But now you have on-cycle symmetry. So the on-cycle symmetry says that if you have the Brownian motor, you have also the refrigerator. What is the refrigerator? I take this object and I apply to it a torque. Well, the theory tells you that because of the motion induced by the torque, this object will transport heat from there to there. It's in thermal contact here, it's in thermal contact there. On-cycle symmetry tells you that actually, so if you apply a torque to this chiral object, you will have a heat flux. So it exchanges energy here, but the energy balance is not perfect. Because of the torque, there will be a heat flux, which we calculate. We have explicit expression for this, and we calculate even for having an object of a specific size. Newton meter on which you apply torques of piconewtons, and you get very reasonable heat fluxes. We verify it, I'll show you, we verify it also, not the rotational one, the translational method one, we verify with molecular dynamics that this heat flux is there. So it means if you have a chiral object and you apply a torque to it, then the object is transporting heat from one side to the other. So it's a refrigerator. It cools down one side and heats up. And I'm still waiting for experimental verification or real technological verification. I wanted to mention this because it was something that I did a few years ago and I found really interesting. Okay, this is subject number 1. I mentioned for those who are interested, they can talk to me if they want. Now I'm coming closer to my main subject, which is the second law. And as I mentioned, the second law is intimately related to this concept of Carnot efficiency. So remember, if you have two reservoirs at different temperatures, you can in principle find some construction in which you transport heat from hot to cold, and in the meantime you get out work and the maximum efficiency. So first thing I will not mention in detail, but there has been a lot of discussion on whether you can reach Carnot efficiency for such fluctuating small-scale constructions that I mentioned. And so I call that this thermal drying mode. Like for instance, Feynman-Smoluchowski construction or my construction. In my construction and Feynman-Smoluchowski construction, you will far away from Carnot. You don't get quite near Carnot, 1% or even less than 1% Carnot. But it is possible to reach that. So there has been a lot of literature again, which I skip here. I just want to mention to you that it is possible to reach Carnot efficiency even with small-scale engines operating continuously and so on. It's a subject I will. What I want to tell you about very quickly is that there is another very interesting question, apart from the question of Carnot efficiency. Why? Carnot efficiency is reached, as I mentioned, if you work reversibly, that is very, very slowly. If you work very, very slowly, you get work, but it takes forever, so the power is 0. Okay. Then you can ask the question, I want power, so I have to go out of the reversible regime, out of the very slow regime. As I go out of the very slow regime, of course, my power will increase. I start with power 0 when I'm very slow, it will increase. And you expect, of course, if you go too far out of equilibrium, the efficiency goes down. So actually, your power will again decrease because the system becomes very inefficient. And this is the question that I'm asking. So I go out of equilibrium, I look at the point where the power reaches a maximum, and I ask what is the efficiency here. The efficiency will obviously not be Carnot, because Carnot efficiency is reached only in the reversible regime. But I go out, and so I want to mention, and again it's not the main topic here, I just want to mention for those who are interested, that there are universal results for this efficiency. Let me first mention this result. So this is a result that I derived a few years ago. If you use the linear irreversible thermodynamics. So this is the theory by Prigogine and Onzaga. This allows you to study what happens close to equilibrium. And you can study the question, it's 4 or 5 lines calculation. I will show you that on another slide. You see that indeed as you go out of equilibrium, your power increases and then goes to a maximum. And actually the power is maximum when you apply half the stopping force. Those who maybe are a little bit familiar with this question. And the efficiency turns out to be at most half of Carnot. At most. And to get half of Carnot, you need that the Onzaga matrix has a zero determinant, which basically means you have two fluxes that if the determinant is zero, you can have the fluxes are zero even though the forces are not zero. So that's a very interesting situation. This is a situation unique. If you have that situation and the two fluxes are proportional, then the efficiency at maximum power will be. Now then the question is of course what about nonlinear? Because this is I forgot to say, this one half in fact comes from Onzaga symmetry. Onzaga symmetry comes in fact from the reversibility of the underlying laws. So in a sense you can say this is a trace of the reversibility. So ask what is the efficiency at maximum power in the linear regime for the best efficiency you can reach is this one half, the value, this 1/2 comes from reversibility. Now we were able recently to show that if you go to the next order in this expansion, you find again a universal coefficient, 1/8, but there is an additional constraint. You need that the system has to have a left-right symmetry, so that if you, I'll show you some examples, if you let it operate in the other way, it has the same configuration. And again, you find 1/8, but now you see this is related to Onzaga symmetry. This is linear irreversible thermodynamics. If you trace it back, this 1/8 comes from the main part of my story today. It comes from the fact that there is a new formulation of the second law. So you can derive this 1/8 from what is sometimes called the fluctuation theorem, which will be the main topic I will talk about. I just want to mention this because it's interesting, these connections, so that these issues of efficiency also point out to the fact that there is apparently a deeper way of describing the second law than the way that we have done so far. So just this slide, these are all kinds of models in which you can calculate efficiency at maximum power analytically, and you see the expansions here, you see the 1/2 and 1/8, 1/2 and 1/8. Here you don't see the 1/8 because the system doesn't have left-right symmetry. So there's a lot of activity now on this issue of efficiencies at maximum power. So I come now, you erase everything, you relax and take a deep breath. And now I want you to tell the main story and the main result. Okay? To tell you, so I want to show you how we should reformulate the second law. Okay? And to do that, I will use a very specific scenario because this scenario makes more connection to the concept of work, mechanical work, which is something that we can understand very easily. So the scenario that I look at is the following. This is what you normally also see in the textbooks of thermodynamics. I have a system, for instance a gas, that I'm going to change the state of the system from an initial configuration, which I call A here, to B. So the system changes, initially it's in equilibrium state, it's in contact with a reservoir at temperature T, and I'm going to change the system from A to B. I'm interested in the amount of work I need to put in to do that. This is my work I put in, this is an algebraic number, so this work could be a negative number, of course. If it's a negative number, it's interesting, anyways. I'm interested in how much work I need to put in to change the system from state A equilibrium to state B equilibrium, while it is in contact with a feedback. Now you know, of course, from thermodynamics, I mean, I'm just reproduce this very quickly here, this result. You know from thermodynamics, of course, that this is not a state function. The work will depend on how you do it. So we can only expect that there is an inequality that tells you something about the work. Now, let's do it. So what does thermodynamics tells you? in this entire world, the entropy can only increase. What is the change of the entropy in the heat bath? That is, of course, the heat that it takes in. Q is the heat to the system, so minus Q is the heat to the reservoir. So this is the change of entropy of the reservoir. Then I have conservation of energy. The system energy changes because it receives heat and because it receives work. And then I introduce this quantity F, U minus Ts. Okay? What is the change of, from this this is the system entropy, I can find what is the system entropy is given by this expression. So what the second law tells you is the sum of this guy plus this guy times T, say, has to be positive. And if you calculate it, you find this expression. So this is just a very simple thing that you see in thermodynamics. So what does it tell you? The amount of work you put in is at least the difference in free energy. I have an initial state, equilibrium free energy, final state, equilibrium free energy. And the amount of work I have to put in is at least this number. It can be more, but not less. And it's equal to delta F when I work reversibly. When this is 0, this means at no point do I produce net entropy, then the work is equal. This is the second law. This is the way of stating this. But look now. Let me do this experiment here, not for a macroscopic system, but for a small system. I take here a real experiment, and I will actually show some results, but I have an RNA strand which I attached on both sides, and I'm going to move this. So the system is initially at equilibrium, like the piston, in this state, and I'm going, this is me of course, I'm going to move to another position, and then wait, and I reach another equilibrium. It's exactly the same experiment as I do there. And when I move, I have to do work. But of course, you know that in this experiment, the amount of work you will do will change. It will not be the same all the time. It will be actually even inside. Maybe sometimes you receive a kick, so you actually get work. So there will be, in this experiment, and we show some examples, you can measure actually the probability distribution of the work that you spend when you move from one initial equilibrium to another final equilibrium. So clearly then you wonder, but what is this? What is the relation between these guys? And if you ask people, so the answer is clear. They will say, well, you have to put a lot of these guys in parallel, and then you have like a real macroscopic strength, and the work you will measure will be the average. And so this is the second law. The second law tells you that the average work should be larger than the difference in free energy of initial and final state. But then you are a little bit surprised. I mean, how can it be that such a basic fundamental law tells you only something about an average of a probability distribution? That looks very funny to me, right? I mean, some very basic property has to do with the average of some distribution. What about the distribution? Does it have something? I mean, is there something? Okay, so we'll see that this is the point. Now, you can of course now wonder, well, this is all fine, but I mean, is this important? Yes, it's important, even technologically, even experimentally, because people can measure this, they can measure, following a trajectory, these very strange steps where actually the system does something that is not in agreement with the average increase of entropy. For instance, here are steps of the ATPase, which is driven by a chemical gradient. So actually it should always rotate in one direction, but sometimes it takes back steps. It goes, there are places where this small engine is turning against the chemical gradient. So actually it's doing opposite of what the second law predicts. Here, another example, single electron transistors. We have a difference in potential energy. Electrons should go, I mean, from the current goes from high potential to low potential, but sometimes it does the opposite. Okay? And so you have these fluctuations. So at least first you have these quantities. They will depend on the trajectory, and sometimes even it looks like they are not doing what they are supposed to do. Okay, now I will tell you what is the result. Okay? Unfortunately, I don't have time to give proofs. There are now many derivations. And as always, when you find something very basic, you can find many derivations, and I think at this point, actually, nobody has found maybe the derivation that kind of incorporates everything, and there are still some issues which I mentioned. But I will just first tell you what for me is the basic new result, new understanding that we have reached. So to do that, so what I would like to show is that I have an expression for this quantity W, for the work, okay? So I'll go back to this. So I do the experiment, I have a certain amount of work. I do another experiment, I have another amount of work. I do another experiment, I have another amount of work. I would like to give you the expression for the work, given the experiment. Okay, so, and what I need to introduce is the following. So if I do an experiment, I see the system is doing some things. It has a trajectory. I do the experiment again, it has another trajectory. Every trajectory, in principle, you can measure the probability for observing one of those trajectories out of all the possible ones. But many, so repeat, the system does something else, does something else. Now what you have to do is, when you do the experiment, you have also to do the reverse experiment. So, for instance, when I go from A to B, I have to do also the experiment going from B to A. When I stretch, I also have to do then I have in the other experiment, of course, the system is doing, sometimes it retraces the steps, sometimes not. I have to ask, what is the probability for a specific path in the forward case, and then I have to ask, what is the probability to see that same path run backwards in the backwards. This I call P-Q. And then the main result is here. My claim is the work. So this path here that has a probability P, when you do it, it has a certain amount of work. Well, this work minus the difference in free energy of the initial and final state divided by the temperature of the reservoir is the log of the ratio of the probability of seeing this path in the forward experiment divided by the probability of seeing the path in the backward experiment. This is the result. This result can be derived basically only because micro-reversibility and Liouville theorem. Nothing else. So you need to have, so the Liouville theorem is valid also in quantum mechanics, micro-reversibility also, and it's also valid even if you have relativity and so on. I think it's always valid. So I think this result is completely general. Okay? Quantum mechanics is a little bit, well, you have to, let's okay, not go into the details. So okay, but let me give you an example, okay, because maybe then you will understand better what I mean. I have here the experiment with the piston. I start the system in equilibrium. I go from here and I go to a final state here. And now I look at one particular realization. The particular realization is I know where all these guys are and I follow them and they go there. Okay, so this is a particular realization. This realization here has a certain probability. Okay, this is actually a typical realization. Okay, so it will have a relatively large probability. Now, if I am doing this motion very slowly, let's now look at the reverse experiment. So I'm now pushing this thing back, and what I'm asking you, so I have a certain probability to see this, I'm asking you, what is the probability of seeing the reverse image here? So I only have, of course, here the positions of the particles, so I also need to reverse. So I'm asking what is the probability to see this in the backward experiment. Well, you see, actually, these two are more or less, if this is a very slow process, these two probabilities will be more or less equal. And, therefore, the work that you need to go from there to there will be equal to the difference in free energy. If you, however, move very fast, a typical forward trajectory, so one which has a reasonable probability, will be this one. My formula tells me I have to find the probability of seeing this thing in the reverse experiment. Because this is very unlikely. You see, you actually think that all the guys in the beginning already are sitting in the left-hand side. It's very unlikely. So this guy is very small. It's actually exponentially small. Because you need all these guys to see. So this guy is exponentially small, and the ratio of this is something that is exponentially large. You take the logarithm of it and you find an extensive quantity. It's the entropy production of this process. This entropy production associated to this. Okay. So now you can of course ask, what is the relation to the normal second law? So this is, I've given you the formula for one run of the, so one specific thing that the system does when I go from A to B. It's not an average, it's for a specific trajectory. The second law is a statement about the average. So how do I find the average? Well, the average is, I have this quantity for a specific trajectory. I have to, the probability for a trajectory I call P. I sum over all the trajectories, and I have the average. Well, this quantity here, for those who are working in information theory, they will recognize the relative entropy. It's something that's always positive or zero. Very easy to show with Jensen's inequality or whatever. So the fact that this average here is always positive is a byproduct. It's a byproduct of this specific shape that I gave you, this expression for the entropy production. Automatically the average is positive. You see, this is what I was alluding to in the beginning. How could it be that an average is a really profound property? It's not a profound property. I think this is the profound property, that the entropy production is a log of the probability of the forward experiment divided by the probability of seeing the trajectory back. By the way, this gives a very nice interpretation to this entropy production here, because this is only zero when these two guys are identical for all trajectories. This is a sum over all trajectories. This quantity is only zero when the two probabilities are completely identical, which means there is no direction in time. The probability of seeing some trajectory and the reverse trajectory are exactly equal. There is this full detailed balance. You cannot see direction of time. So whenever in your system there is an asymmetry in the forward, so I give you I give you runs. If you can detect the direction of time in these runs, then you have entropy production. This is what this form.
Let me say something. When you do that very slowly, you do that function.
Then P and P tilde become equal.
Then I understand what. How come when I do the reverse trajectory, the reverse process, pushing, I find the same macroscopic trajectory?
The probability for the reverse trajectory is equal to the probability for the forward trajectory. Yes, they become equal. So in this case, so what I'm saying is, if you have this forward run with all these speeds and so on, what I'm saying in a system where this is very slow, the probability of saying this is equal to this P and P tilde R. P and P tilde R.
When I reverse, there will be some particle which have a different velocity.
No, but all the parts. So I have the reverse velocities here also.
Yes.
So it just retraces its steps. Maybe it's not always true. Okay, this is what.
Does the P depend on all internal variables?
Yes. Okay. I could also say because we. So in principle, the P depends on everything, but very often many degrees of freedom are at equilibrium. They don't have an error of time, and so you can actually take them out. So this is another story. I can from such microscopic formula derive. People have derived these results for the first time for Markov closures. We derive them for Hamiltonian dynamics, and it's the same formula. And how is the connection? The connection is, so in Hamiltonian dynamics, P is the trajectory of the entire system with all the coordinates. In a stochastic description, of course, it's only those coordinates that appear in the stochastic description. This is consistent because in stochastic description, you assume the other variables are turbulized. Those that are out are turbulized. And when they are turbulized, they don't have an error of time. They fall out of this formula. You can integrate them out, and you will go from the microscope to the stochastic expression, which is the same formula. It's the same, but it has much less variables. So actually, one of the things we did in one of the computer experiments is if you try to measure the entropy production and you do it not very well, you don't go into all the variables, you underestimate. So you have to catch all the errors of time to get this full expression. Otherwise, you get no error. Okay, now let me briefly tell you two results you may have heard, which follow from this result. So this, for me, is the basic result. Now you may have heard about recent developments about what they call the integrable fluctuation theorem. All the work there, and it's actually the same. So what has this to do? Well, if I have for this fluctuates, so this depends on the path. So I have now an entropy that depends on the path. If I take minus sign here, then these two guys switch. I take the exponential, the log goes out. So I take p tilde over p, and then I average this quantity. So the average is, of course, with the forward probabilities, the probabilities for the paths. So this is what I do. I have this quantity is this. I average over p, which is basically sum of all the trajectories with p. This goes out, but this is also a probability distribution. This is a probability distribution for the backward, but it's normalized, so this is 1. So if this formula is correct, and I measure this quantity, or this quantity, this is something, you see, I like this presentation. This is something well defined, this is defined, these are the temperatures of the bath, this is the free energy difference initial and final state. This is something you can measure, it's work, it's energy. So if you look at this quantity, and you take exponential of minus this quantity, and you average over all the paths, it should be 1. This is actually the integral fluctuation term, or I have it here. So if you bring this guy out to the other side, you get this famous Jarzynski equality, which I didn't write up here. So exponential of minus beta work average is exponential of minus beta delta f. Okay, another thing you can do is I write this is equal to 1. This average is equal to 1. Well, this is this average. The average is the probability for this quantity multiplied by this quantity integrated all the variables of this quantity. This is 1. Well, this here, this quantity here, is a positive number which is normalized, so it's a probability distribution. And actually, so the reasonable thing to do, it's another probability, so it's a p tilde, and it turns out, this takes a little bit, one more slide, so I don't mention it, but this turns out to be probability distribution for minus ds total, and this is equal to that, and therefore you get what is called the deviant fluctuation. So this property implies that the probability distribution for this quantity divided by the probability distribution, the backward experiment of minus this quantity is exponential of this quantity. Now, in words, what does it mean? To observe a certain entropy change in the forward experiment is exponentially more likely than to observe the corresponding entropy decrease in the backward experiment. This is called the fluctuation. So, now this is very abstract, so okay, there are a lot of references there, so I give you kind of very quick introduction in what people have now been working on for 50 years, so there are many versions. But maybe it's good to give illustrations when you give such results, okay? And the easiest illustration, so this is the detailed fluctuation theorem, but you can write it for the work variable because this is something you can measure and you write it in this way. This is called the Cook's equality. So what does all this mean? So I do an experiment and I have some work and I repeat the experiment, I get a probability distribution for work. I do the backward experiment, so it's the reverse one, and there I also measure the work. And then this fluctuation theorem would imply that if I divide these two probability distributions with a minus sign, I get this expression. Okay? This is the result of this. So they did real experiments. These are one of the most beautiful, I think, results in the field. It's people in Bustamante's group in Berkeley. They did real experiments. The experiment that I showed you, they open the RNA hairpin and they close it. They open, they close, they open, they close. During the opening and the closing, they have force versus extension, and force times extension is work, so they can measure in every run how much work, and they repeat. And they plot the probability distributions for the work in the forward experiment and the probability distributions for the work in the backward experiment. Actually, they didn't you can check that this is really satisfied, but in their plots, but the only thing they check, because that was what they were interested in, is you see, this is kind of amusing. This probability distribution as a number is equal to this number when the ratio is 1. This is when W is equal to delta F. So these two probability distributions should cross in the point W equal to delta F. And so this independent I mean, this is a general result. It doesn't depend on how I do the experiment. So I can do the experiment very slowly, I can do it fast. So they do this experiment in 3 speeds. So these are the 3 colors. And this is the probability distribution for the fastest one. And by the way, you see, as you do it slower and slower, as I mentioned, you go to the reversible scenario, and your W will become equal to delta F, your probability distribution will equal to delta function. So this is, and as you move out, so this is of course more and more non-equilibrium, you move faster, distributions broaden, and they cross indeed all at the same point, which appears to be a very good estimate for the difference in free energy. So this is what people are, I mean, actually Chris Jarzynski, who found this first Jarzynski quality, was interested in it because he wanted to have an estimate for delta F. That was the main purpose. People are still working on that. Okay, another experiment is a computer experiment. This was a real experiment. Another experiment is one that we did. We basically did the Joule experiment again, but with a small, very small system for a short time. So what do? We have an arrow which we move from one position to another with a certain speed. Forward and backward, we move the arrow backward. Okay? And you can do that in the computer, and actually, if this is an ideal gas, so in the paper, which is here, we also we can calculate the probability distribution for this work analytically in the case of an ideal gas. And we can explicitly show, of course, because we have analytic results, that these relations are satisfied. But it is very interesting, of course, to do experiments with this is with hard disks. So we did experiments with hard disks. And I show you the plots, just to give you an idea of, this is the forward process, this arrow, this is the backward process. Here I move, the speeds are expressed in terms of thermal speeds of my gas particles. So I move here at 0.2 the speed of, thermal speed of these guys. Okay, so it's quite fast already. And I move over, I don't know, I move 50 time units, which is over 10 times the diameter, I think, of these guys. And I do the measurement, well, we have a theory also, and this is the probability distribution of the work. Okay. Now I should tell you, in this case, there is no difference in free energy. When the arrow is here initially, or the arrow is there initially, it's an infinite system. There is no, this is the same state. So there is no difference in free energy. So according to the second law, to do that, your work should be positive. Larger than the difference in free energy. So, and you see, of course, that most of the time the work is positive, but you have cases where the work is negative. Sometimes you get kicks in the back, and you get work, even though you're supposed to do work.
I have a very basic question. If you're calculating this with respect to probability distribution, it's a probability distribution over realizations. You do the same thing many times?
Yes.
And what do you change?
Just the state of this gas, these particles have speeds and positions which are initially sampled from an equilibrium distribution. So this is pure Newtonian dynamics with periodic boundary conditions.
So
what changes is
just changes the initial condition.
You start in equilibrium, so everything is in equilibrium. So your particles, but of course the particles have distribution in space and in speed as prescribed by.
So our initial condition sampled an equilibrium distribution of the gas.
It's an average over the.
But then when you were talking about the probability of a trajectory and the probability of the reverse trajectory,
Yes.
what do you mean? It is not the probability of a trajectory.
Okay. From a microscopic point of view, the trajectory, the probability for a trajectory is essentially related to the probability of the initial state, because that's exactly. So the Hamiltonian way, this is the way we do it. If you have a Markov process, it's slightly more complicated because you have noise, of course, and so you have really trajectories that develop in the course of time. So it is, in principle, from Hamiltonian point of view, it's just a probability with respect to the initial distribution. But in
the Hamiltonian system, the probability of a trajectory is the probability of the initial condition. So it is not the probability associated with dynamics.
But then I calculate. This is. I have to reduce this to the probability of what I want, which is the work. So it is true that for a given initial state, I can calculate, I move my arrow, I can calculate how much work I have.
But then when you calculate the probability of what you call a given trajectory and the reverse trajectory, you crudely calculating the probability of the initial condition for the trajectory and the probability for the initial condition for the reverse trajectory. But both initial conditions come from the same distribution.
No, because you are at the end in different state. Okay, you should we can talk. This is the way we did in the PRL. For the Hamiltonian case, is exactly because it comes out in 3 lines. It's exactly that. So for Markov process, it's somewhat. Anyway, so let me repeat again. You do this, you have, as Maxi mentioned, your initial distribution is equilibrium. So this means you sample positions and speeds. You did the experiment, and then you repeat, and you get a probability distribution for the work. You do it there. In the reverse experiment, as you expect to need much more work for the same speeds. This is against speed 1/5 of thermic speed, and this is twice sonic speed, if you like. This is also twice sonic speed. So of course, if you move faster and faster, more and more work, and the structure becomes very complicated. Look here, in this experiment, so I move on. This moves with the twice average speed of the gas particles, and this is the probability distribution of the work. Okay, and they look, of course, very highly nonlinear. Well, take the log of the ratio and plot them, and you find that they obey the relation. So these two. So I would never have thought 10 years ago that this had anything to do with this, but it not only has anything to do with it. This can depend on the ratio given by this function.
No, but I mean, you can make very simple experiment. You put in the middle of your box distribution, and then you calculate distribution forward and distribution backward. And this is the point. This is what Max says. I mean,
yeah, of course. Okay, but then okay. They might be already with C, actually.
Yes, but you're here.
Chris, is not an analysis.
Okay, so, you can derive this result for stochastic processes. You can derive it for Hamiltonian systems. For Hamiltonian systems, it is true that it's related to the probability of the initial states and final states. And it's exactly related to what you said. It's a few lines I can show you after we talk how it goes. But let me maybe continue, because I'm running out of time. The third experiment I want to show you, this experiment I show because I want to convince you that I believe this is a very deep result. So you can prove it Markov, and you can prove it Hamiltonian, you can prove it in quantum mechanics and so on, but I think it's more general than that. And so one of the things we have learned from our ancestors, previous age, maybe century, is that Einstein, that you have to do thought experiments. Let me show you a thought experiment. This is a thought experiment where I have 2 boxes, black boxes, at different temperature, initially at equilibrium, TA here and TB there. So systems are initially, my experiment is what? I open a window where I only let pass photons of one specific frequency, call them omega naught. So I open this window for a short time and I close it again. What happens is, during this opening of the window, there will be photons going from left to right and from right to left. So there will be a net amount of photons, let me call them dn, that go from this side to that side. So this is the amount. So this then will be the amount of energy that has been transported during this experiment from one side to the other. After I've closed, system relaxes to equilibrium. And so I have an entropy change in the system, which is known the amount of energy that it has received divided by its temperature. So this here is the expression, and I forgot to write the as total. This is the expression for the entropy change in this entire unit, in this entire system, during this experiment. Obviously, this quantity is a random quantity because this is a random quantity. And now we have a very interesting connection. We see that the probability distribution of this quantity is related to the probability distribution of this quantity, which is a photon count problem, which you find back in. So I'm not at all an expert in photon count quantity. So the first thing I did was I made a mistake. I said, okay, I'm going to calculate how many photons go from there to there. I know the density of photons because it's Planck distribution, and I assume they arrive at random. I do some calculation, and I do the same on the other side, and I try to verify this theorem. It doesn't verify. And then I asked the people, but you have photons, they are not random, there is photon bunching. You have to go and look at Harvard-Twish and Larborg calculations, and they will give you the correct expression for the photon count for a black hole. So I go, I put in the negative binomial is the one that Glauber derived for the statistics of the photon. I put it here, I put it there, and I find back that the fluctuation curve is very flat. So this photon bunching has to do, this is a quantum field effect, and if you put it in, you find that the fluctuation curve is very flat. So my last slide, I will only very quickly flash it because the last slide is this, some recent work also that I did with Massimiliano Esposito, is now in Luxembourg. So I mentioned to you this fluctuation theorem, okay, for the total entropy, which is a very basic quantity. So, but we were able to show that actually you can split the entropy production in two quantities, which I call adiabatic and non-adiabatic, but the meaning is one part of the entropy production is due to boundary conditions, and one part is due to driving. And why is this interesting? It's interesting because we can show that both of these quantities separately satisfy also a theorem of that kind. Slightly more complicated, so this is the normal theorem. Here you have to calculate the probability distribution where you reverse the time schedule, but you're also having some way to reverse the boundary conditions. This is what this cross means. And this here, you only have to reverse the boundary conditions. And then you find that these separate quantities also obey a fluctuation theorem, they obey the integral fluctuation theorem, and they separately increase. So what gives you the impression is that you can split the second law, the entropy production, in some part it has to do with boundary conditions, and some part it has to do with driving. And of course we still, wondering whether there are more implications to this thing. Are there three, is there more than one second law? So, of course, this is the fact that you have splitting. This kind of thing is not completely new because we know in linear irreversible thermodynamics that you can sometimes write entropy production as entropy production due to viscosity, to the thermal, and so on. So here it is at a very basic level that we are able to do this. Okay, so this brings me to the end. So why do I talk about many phases of the second law? I started with the old phases, which is no efficiency, of course, the entropy increases. On-cycle symmetry is also related to this issue. And I tried to show you that there have been recently very interesting new developments. There is a kind of universality. Also, like you have Carnot efficiency, you have something, new interesting object, which is efficiency at maximum power, which has some universal features. And then, of course, there is, for me, the new way of saying the second law is if you have a trajectory, associated to a trajectory, there is a quantity which I call stochastic entropy production, which is the logarithm of P over probability for the trajectory divided by probability for the reverse trajectory. The average of this quantity is the normal entropy, and this is positive. But this quantity obeys symmetry relations, so the probability distributions obey, for instance, this detailed fluctuation theorem, and we are able to split it. Now, why is all this interesting? This is very interesting. Of course, we have lived 150 years with the average only, and we didn't bother about fluctuations. But of course, now we have reached a time where we can technologically do it. We are measuring things. Biology seems to be working with fluctuations, and so there are a lot of new questions that we can address. I mentioned, for instance, what I find interesting is this Brownian refrigerator, that you can sometimes find new principles for old questions, like the question of refrigerator. Now, there are still developments going on right now. The development is going on right now in this field is that we can go back to the question of Szilard. So Szilard says if I have an intelligent being, I can kind of beat the second law. The answer to that is that you have to describe the intelligent being. So you have to do that. And so we are now able also to do that. So we are able to include in this quantity, which is normally work minus delta F over T, we can include the effect of information, and it's all consistent. So if you give me an initial distribution that is not in equilibrium, I still can tell you what will happen. So this is something that we are working on now. And of course, I have not worked so much on it, but of course there are very interesting questions related to the formulation of this theory in the field of quantum mechanics. where you have, of course, the funny things, you have quantum coherence, and you have decoherence is related in some way to the error of time, or the measurements related to the error of time. So I think there are still deep questions to be answered there in the context of quantum mechanics. So this is where I want to stop. Thank you very much.
Any questions?
Yeah, I mean, the first of all is similar to the Hasselt probability and by explaining it that way. So, probably I think that this image work because in your statistics on your measurements are just only probabilities which are near equilibrium.
No. You don't have to be near. I'm moving an arrow here at twice the speed of sound. This is not equilibrium. This is very far away from equilibrium.
No, but you said that the particles were
Initially.
Parallel, yeah.
Initially, okay.
The initial and the final states, they are always at equilibrium.
No. So, in the classical formulation, okay, so there are, of course, I didn't have time to really discuss. People have developed fluctuation theorems for steady states. Then you have fluctuation theorem where you start in equilibrium and you end in equilibrium. That's where many people are. But actually, you don't need all of that. You can start anywhere and go anywhere also. You can do that. So all these limitations are not, you don't, it's not a problem. Okay, I can tell you.
Do we know that consider beyond,
well, the one over this, very good question. So I mentioned the 1 over 2, efficiency at maximum power, 1 over 2 comes from on-cycle symmetry. The next term comes from the generalization of on-cycle symmetry to the nonlinear response. So, I don't know if you know, but at the level of, so you have reversibility of the laws of physics. This gives you something. This gives you one number, so to say. Okay. So in on-cycle symmetry, this one number allows you to link L12 with L21. At the next order, you have, of course, many more coefficients, and this one condition doesn't do enough to tell you something. That's why I mentioned you need two extra things. You need strong coupling, which is basically the two fluxes are proportional. This is an additional constraint. Plus left-right symmetry. If you take these three things, you get a number again. So the reversibility comes again. And you can, in a sense, you can derive these things from the fluctuation theorem directly also. But this is nonlinear response. The fluctuation theorem was way, this is the point. We go way beyond linear response now. We can actually go as far from equilibrium as we want. Then you need a microscopic theory, and every broken arrow of time, even at the level of microvariables, will be in the formula. That's what I have with P over P tilde with all the variables, and this will be the answer to production of data today. Depends on the specific trajectory. You have trajectories that are very breaking much symmetry, but you could have situations where if you're very far from equilibrium, you did experiment, the work is delta F. Why? Because by accident you happen to do a realization which has no error of time. It can be there. It's unlikely. So there is no limitation in the distance from equilibrium.
I don't understand this distinction between the reversibility from the boundaries and from the driving. I don't know, for example, you show the convection. What is the driving apart from?
Yeah. You don't even need driving. So if you the simplest experiment, you start from non-equilibrium and you go to equilibrium, you have entropy production. This is one contribution. Then you have the other contribution when you have boundary conditions. So then, of course, you never go to equilibrium. You have an entropy production. When you have both at the same time, suppose you have boundary conditions, and on top of that, you start in a non-steady state regime. You have two contributions. Each of these contributions, yes. So we can kind of separate out always two contributions. One we say this is related to the boundary conditions. The other is related to the value. Because if you take out one, this is the one that remains. If you take out the other, this is the one that remains. Of course, when they are both there, we have the formula, and we tell them, well, this is the one related to the boundary. Because of course, they intermingle. The dynamic is one dynamic. But it turns out that you have these two quantities, which separately have all the properties of the total entropy. So at the level of fluctuation, so very deep level. Let's see.
In your photon count experiment, so is the bunching statistics the only one that gives rise to the fluctuation theory? Have you checked that, or you're just
I
comparing?
have not checked if any other statistics would not do. It's true, I have to check that. I want to, but it was, yeah.
What do you think after doing, because I don't know the paper, but after doing the calculations, do you think that this is going to be, is there something deep?
You could maybe find an accidental. So the point is you have to, I don't. So it depends. So you all of course need probability distribution for the delta n. Of course this has during a certain time. So the problem is when photons come, the next one doesn't come independently of the previous one. So of course your question is quite complicated. You could ask, if I have a very general statistics, can you still prove that the only one satisfying the fluctuation theorem is the one that, I don't know. I mean, it would be interesting to check.
Any questions? If not, this will be here until Thursday. He's occupying an office in the third floor, so we'll go from here. Okay, thank you.
Yeah, just 3 questions. Yeah, my name
Observe it for very long time, and you take several look all kinds of trajectories. What I'm saying is that you will find one trajectory as equally for any trajectory you will find if you find this time then there is no on average delta S is 0. The specific delta S is 0 probability.
Okay, second naive question. I mean, when you mentioned that you have this box with you have box with T2 and which I really didn't understand T2, T1, and because I have Brown motion.
Intuitive explanation. Okay. Suppose that this T is 0.
But this is always larger than this.
Yeah, no, it doesn't. Then it moves in your direction.
Okay.
So, but suppose this T is 0 and this is large. Actually, this was the case that I had. Sorry, T is large. So what happens? So when the guy hits, of course, it moves.
You're right. But I have a